In the last few videos, you've seen many references to layering, particularly in the video describing the 4-layer internet model. Layering is a very widely used principle and has been used in networking for decades, predating the internet. In fact, layering is a design principle used widely outside networking as well. It's commonly used as a design principle in many types of computer system. There are lots of reasons for layering, and we'll explore some of them in this video. We'll explore what layering is, we'll look at some of the simple examples of layering in communication and computer systems, and we'll explain why so many systems are layered, either by natural happenstance or deliberately by design. Let's start with a definition of layering. Layering is the name we give to the organization of a system into a number of separate functional components or layers. The layers are hierarchical and they communicate sequentially. In other words, each layer has an interface only to the layer directly above and below. Each layer provides a well-defined service to the layer above, using the services provided by layers below and its own private processing. There are many examples of layering in everyday life, particularly when one service is deliberately or naturally layered on top of another. For example, if you're looking for airplane tickets, you might visit a brokerage website such as Google Flights, Hipmunk, or Kayak. These websites let you find tickets across a wide range of airlines by communicating with a single service. You could instead go to the website of every airline to query what tickets they have available. The brokerage website is providing you a service layer on top of each airline, abstracting away the details of each airline's website for you. Now, if we look under the covers of each airline, they fly different types of airplane over different routes. The airplane takes care of the details of providing the service and offers you the simple abstraction of a ticket valid for a particular flight to take you between two airports. They're hiding many other details too, such as how they provide the awful food they serve. In many cases, they have a number of suppliers to provide meals, drinks, fuel, and so on. Each of those are naturally hidden from us, the consumer. This separation of concerns allows each layer in the hierarchy to focus on doing its job well and provide a well-defined service to the layer above. Another well-known example of layering closer to the internet is the Postal service. Imagine that I have a book that I want to send to Phil. I place the book in an envelope, add Phil's address and mine, and then hand it over to Olive to take to the mailbox. The Postal Service sorts the mail, then sends it by a variety of different means, airplanes, mail trucks, trains, etc., until it reaches a sorting office near Phil. The mailman delivers the letter to Phil, who opens it and finds the book inside. The service is clearly layered. At the top, I don't care how the letters get from me to Phil, whether they go by airplane, truck, or hovercraft, and I don't care about the route that the book takes, or how many sorting offices it passes through along the way. I don't mind whether Olive walks, skips, bicycles, or runs to the mailbox. I don't care which mailbox she posts the letter in. I want the lower layers to abstract away the details for me, providing me with a simple service model. I put the book in an envelope, and the layers below deliver it to Phil. In turn, Olive doesn't need to know how the Postal Service delivers the letter. She simply communicates with the layer below by posting the letter. Phil just wants the book. Notice that each layer communicates only with the layers above and below. If the Postal Service deploys new trains or starts using a different airline freight service, Phil and I don't need to know about it. In other words, because communication is simply up and down with a well-defined interface between layers, we can improve each layer independently over time. For example, if I want faster guaranteed delivery, I could hand the envelope to a carrier such as DHL or FedEx. The interface is almost the same. I simply give them an envelope and money.
Layering is deliberately designed into many computer systems. When we write programs, this is TY editing a program, we create source code using a language that abstracts away the details of the operating system, how virtual memory works, and how the low-level details of the hardware. Okay, so C isn't great at hiding the details, but many other languages, such as Java and Python, deliberately shield us from how the lower layers work. As a programmer, we communicate with the layer below, the compiler, by handing it our source code. The compiler is a self-contained functional component that is responsible for several tasks, such as lexical analysis, parsing our code, pre-processing declarations, and code generation and optimization. The compiler generates object code, which it then passes to the linker. The linker links together the compiled object files and libraries. It generates an executable file. The CPU, real or virtual, then executes the code. If you have experience writing computer programs, the benefits of layering are fairly clear in this example. Layering breaks down the overall problem of writing programs that execute on hardware into modules or functional components, each with a well-defined role and providing a well-defined service to the layer above. It also provides a clear separation of concerns. The compiler can focus on lexical analysis, parsing, and so on. The linker can focus on efficiently piecing objects together. Neither has to worry about the job of the other, and each can be improved, upgraded, and replaced over time as technology and know-how progresses. For example, we might swap out a commercial C compiler with GCC, or vice versa, without needing to change the linker or the language we use. When Nick first drafted these slides, I was excited that he put compilers in as an example of layering. They're a great example of both the benefits of layering, as well as how sometimes you need to break layering despite the very negative consequences. So let's take the C programming language as an example. Generally speaking, a piece of C code can be compiled for almost any processor. We can take C code like the statement I++ and compile it for an ARM processor and a phone, an x86 64 processor and a laptop, or a microcontroller and an ultra-modern dishwasher. In this way, the C code is hardware independent, and so it keeps the layering here. But sometimes we need our C code to do something special that only our processor can do. For example, an x86 64 processor has all kinds of special instructions that a microcontroller doesn't. C allows you to include assembly code directly. Software like operating system kernels such as Linux and Windows use this for some of their lowest level implementations. The layering that C provides hides this detail so it doesn't let you do so directly, but you have to do so to achieve your goal. So OS kernels include assembly code. Doing so, this means that the code is no longer layer independent. The Linux context switch assembly written for ARM only works for ARM. So you have to write a version of this code for each layer. If Linux wants to run on a new processor, developers need to write new assembly code for that processor. So this is a great example because it shows the benefits of layers that separate concerns and simplify your system, just as programming C is easier than assembly. But sometimes you have to break the layer boundaries. Doing so has a huge cost. Suddenly, you are no longer independent of the lower layer, greatly limiting flexibility. So sometimes you have to do it, but do so only when you really have to. As we'll see, a lot of the practical, operational challenges in the internet today result from people breaking layering and assuming things above and below their service interface. There's a continual tension to improve the internet by making cross-layer optimizations and the resulting loss of flexibility. We'll see one really telling example of this with something called NATs, or network address translators, tremendously useful devices that have unfortunately made it almost impossible to add new transport protocols to the internet.
So in summary, there are 5 main reasons we use layering in computer systems. Modularity. It breaks down the system into smaller, more manageable modules. It's a well-defined service. Each layer provides a well-defined service to the layer above. Third, reuse. A layer above can rely on all the hard work put in by others to implement the layers below. It saves us the time to write each layer whenever we build a new system. Fourth, separation of concerns. Each layer can focus on its own job without having to worry about how other layers do theirs. The only communication is up and down the layers, so it helps keep one layer's processing and data local and internal where possible, minimizing the complex interactions between layers. Fifth, it allows continuous improvement of each function. A sixth benefit is specific to layered communication systems such as the internet. That is, peer-to-peer communications. In the 4-layer internet model, we saw how each layer communicates with its peer on another system, using the delivery service provided by the layers below. Similarly, in the mail example, Phil and I were communicating with each other as users without worrying about how the communication service works.